Just one minute. Is it okay now?
Not yet full screen. I think
Now this is full screen.
this is full screen.
Yes.
Acha. No, I mean the screen means only the lecture part that should come.
Yeah, sir. Actually, you have shared a window only.
Right.
So,
I think that is I need to do full screen, but anyhow there was some problem. Okay, let me do one thing. Yes. Let me.
yeah,
I
please share.
understand that was the problem. Entire
Please,
screen. Yes.
please share your entire screen. Yes, yes, yes.
But that time the share button is not working. I cannot. Uh,
Okay.
so
You know?
that's the problem is coming. That is the reason I don't know
Yeah, you
why
have to
this
again. You have
happens.
to again select it at the top and press OK.
Acha, that let me. Okay, okay, maybe. Right. Just one minute.
In the present button, mark
Right.
a window. Okay. ওই এ উইন্ডো ওইটাতে ট্যাপ করো, তারপরে তুমি দেখতে পাবে
Now
সেই উইন্ডো।
শেয়ারটা কি ক্লিক করা যাচ্ছে না।
Entire
না
screen is working.
Just yeah, I think it's now coming.
Yeah, okay, it's better, sir.
But
Yeah. Now please open your PPT.
is it coming?
না না না, এই তো সে পুরোটাই এসে গেল। হ্যাঁ, নাও ইট ইজ কামিং। ইয়েস নাও ইটস ওকে। So we are now set for the lecture.
Let us
Okay.
wait 3-4 minutes, sir.
That's fine. I mean, the speaker is now set for the lecture. That's the.
Yes. I'm ready. I'm ready.
Okay, you are ready. Okay.
I think it's okay. It can.
Yes. We can see it. Yeah. So you please show your, I mean, yourself first. You put your camera on and
Acha,
then we
camera
can.
is not on.
Your camera? I cannot see your face.
But this camera, I think I make it on.
আচ্ছা, ঠিক আছে, আমারটাকে আমি অফ করে দিচ্ছি। তোমার ফেস দেখা যাবে। আবার তোমার উল্টো জায়গায় চলে গেলে। Again you have gone to the full.
No. That I have done. Is it okay?
Yeah, this is okay. Yeah.
Is my camera working? No.
No, I cannot see your face.
Oh my. I think I make it on. Anyway.
Now you leave the net and then come back with your setting. Camera on.
That can be, but I don't like to disturb that because once again I do it and it will create this problem.
Sir, your video is
Huh?
Video is switched on. It's okay, sir. I think Professor Bhavani, I think your screen is set up is different. I can see Professor Santi very well.
Acha, yes. Okay, Professor Santi, now your video is fine. Okay, Santi, I can see your face. Okay. So Dr. Saw will start at 4:05.
Yeah, yes, sir. Some people are joining.
Yeah. So after just 5 minutes
Yeah,
past 4, we'll start, right?
yeah, yes.
So already 42, 43 people have joined.
which can be a good number.
Yeah. I think, I mean, what is the average attendance, Dr. Sahu, these days? 60 over the
Uh,
last 2 days.
in this meeting, sir.
Yes, yes, the
Yeah,
last 2 weeks.
yeah. Last 2 weeks, in the meeting, almost 80 participants, 80 to 100,
That's
and in
80
the
to
live
100.
streaming, almost 50.
Uh-huh.
So around 150.
Achha. So today also we are doing the live streaming.
Yes, yes, sir. Because the number of students are more, so
Hmm.
uh, we are already on live.
How many have joined the live streaming? Can you see?
Yeah, I can. This the meeting screen is
Ah,
shared on YouTube
that is
Live.
51. Meeting screen I can see 51, including the two for the speakers. Yeah, 51 or 53. I think. Yes. 4.
I think we can start now. Good afternoon, everyone, and welcome to the SOA Lecture 3. I request Professor Bhavani Sinha to may kindly introduce Professor Santi MAITY, who is the speaker of today webinar. Sir, please.
Good afternoon, everybody. I extend a cordial welcome to all of you here to the third lecture in the weekly webinar series, year-long webinar series of SOA. And we are very fortunate here. It is my great pleasure to mention that Professor SANTI Professor MAITY, who is an eminent personality, eminent academician in the field of networking. He has kindly agreed to deliver this lecture today for the web. Professor MAITY actually is on the faculty of the Department of Information Technology, Indian Institute of Engineering, Science and Technology, Shibpur. Since 2012, he is there in that position. He has a very illustrious research career. He worked as a postdoctoral researcher at one of the very top laboratories, laboratory, Signal Systems in France. And Professor MAITY has co-authored many high-quality research publications, including 107 journal papers, 175 conference papers, and he has also edited 21 book chapters. He is really an authority in his area. His research interests include cognitive radio networks, compressed sensing-based image reconstruction and retransmission, digital image watermarking, and secret sharing. And today he will talk on this compressed sensing. His talk is titled as Compressed Sensing and Evolving Technique for IoT Applications. I am pretty sure that all the participants will really be benefited from his lecture, particularly if there are any undergraduate students. I think Professor MAITY will start from the very basics of this particular uh, technique and will also definitely lead us to some advanced topics. Okay, may I request Professor MAITY to start his lecture?
So,
Thank
good
you.
afternoon to all. Thank you, sir. Thank you so much for your kind introduction. Uh, Let me share the screen. Is the screen visible?
Yes, please
Okay.
continue.
So, thank you once again, sir, for kind introduction and nice introduction. And before I go to the talk, I just express my sense of gratitude to Professor Sina for inviting me, and also SWA for inviting me to deliver this talk. The title of this talk is Compressed Sensing and Evolving Techniques for IoT Application. So, as sir was telling that to start from basic, and so what the outline of my talk is something like this. I think all we are, whatever be our background of the engineering field, we are some way familiar with this couple of buzzwords of these days, 5G, IoT, machine learning, and all this. So one such is 5G. If you see the 5G, the telecommunication industry have witnessed a change, particularly in the wireless mobile communication field, starting from 1980s to today's scenario, couple of generation, and starting from your analog communication, very low data rate, not I mean low voice signal, where there was no security issues. I mean, it was open tower, the voice was spread, and it was simply analog voice. From there, couple of change in generation, 2G, 3G, 4G, and now people talking 5G, even beyond 6 and 7G, something like that. But as far as the outline and maturity of the technology is concerned, we are still in 5G away. So the promise and the potential of the 5G, that says, if we just chronologically see that progress in the telecommunication, so it was analog to CDMA, WCDMA, and then WiMAX. Now it's LTE, LTE Advanced. So the changes that we see is basically the first generation. It was mostly coverage dominated. There was a tower and how much long distance it can cover. Then it was the data rate, and second or third generation, along with the voice, there was data transmissions. Of course, the data rate was low, and now it is voice, video, other types of all kinds of data we are seeing in our communication environment and in our mobile or cell phone environment or cell phone platform. And we see that the promise of this technology is the energy efficient, because these all mobile cells are battery driven, and after a certain time we need to go for recharging. And this power consumption, we have already seen on the issues of environment, that tons of carbon emissions are there, because these tiny mobile devices worldwide, billions are there, and they are emitting continuously the power that leads to the issues of global warming. So tons of carbon dioxides are emitting, and that's necessitated us to look for the green communication in the form of that low power energy.
Is there any problem with the communication?
No, it's fine.
But the speaker is not audible, no?
Yes, yes. Yes, mute. Professor Santi, you mute. Yes, yes. Yes, mute. Professor Santi. Sir, in the Google Meet screen, okay, yeah. Please unmute in Google Meet screen. The left side screen. The left side Chrome window. Yes, here, please unmute. Unmute, yes. Okay.
Please speak. Please speak out. Yes. Yes, but this is very weak. I mean, your microphone is not working properly.
It is again muted because of this headphone setting is.
Again, you have muted yourself. Again, you have muted yourself.
Right.
Okay,
Yes.
it's coming now. It's coming now.
Yeah, now we could hear you. কথা বলো আগে কথা no very feeble signal, weak signal. Yes, again you have muted yourself.
Hello.
Yes, now it is fine.
Hello.
Yes.
Okay.
Yes.
Okay. Sorry. So is it now okay?
Yes, fine, sir.
Okay. So I'm sorry for the problem in this. Okay, so as I say in the first slides that the trend in change in communications from coverage dominated to the energy efficient system designs. Now, if we see the visionary in 2020 scenario, that what is expected from the telecommunication sections, that there are different service oriented and there should be many devices, billions of devices to be connected worldwide, and there are service oriented applications to be realized. Our aim to have smart cities, smart home, smart grid, intelligent transportation systems. So what is expected that huge volume of data to be transmitted, latency or end-to-end delay should be very low, and power consumption should also be very low. So 5G requirements, if we see that there are three issues are ultra dense network, ultra reliable communication, and massive machine. As I say already, that what we see in 4G, that up to 30 or 20 like megabit per second data transmission, and that expected that 10 times to be increased. So in the order of gigabits per second, of the order of that to be expected, and 40 terabytes data per user in per month to be there, and 30 billions of nodes to be connected worldwide. So the challenge that comes is the spectrum, how the spectrum can be provided, because radio frequency spectrum is a scarce resource, and if there are billions of nodes to be connected worldwide, and they need a seamless connectivity, so the issue of the spectrum is very, very important issue. Second thing, as I say, these wireless nodes mostly to be battery driven, so they need frequent recharging, or they after a certain time their lifetime should be over, and we need to redesign the network. So energy efficient system design, energy consumption, what we expect energy consumption for today's scenario, that to be 10 time reduction, and end-to-end of the order of near real time, say millisecond of the order of we can expect the delay. So the technological challenge that we are expecting, that data rate to be 100-fold increase, battery lifetime to be increased by 10 times, or power consumption or energy consumption to be reduced by a factor of 10, the volume of data to be enormous, that to be transmitted, and that leads to the promise and potential for service oriented application specific design in the form of, as I already pointed out, and that's made possible because of the promise and potential of the Internet of Things. So Internet of Things is basically that devices like physical objects, these physical objects may be building, maybe devices, maybe vehicles, they to be connected worldwide, and these are heterogeneous natures, and mostly they will provide the cost-effective solution of various services. So the emergence of IoTs, that IoT or the object seems to contain sensing, acquisition, processing, and energy efficient transmission. What we generally see, and why that with respect to the title of this track, that compression or data acquisition process needs a kind of compact representation of data for efficient storage and transmission. Why the existing compression techniques not to be effective or useful, and what we need the compression sensing. I mean, during the acquisition of the data, the means of compression to be there, that I will be talking about. But the reason behind this is what, that if we see the total data generated are much greater than total data storage. We have the storage facility, but with respect to that storage facility, the data generated are much more larger. So we need efficient storage space, but that is again have limited. So what we need to go for compression techniques. Other issues are increase in data generation rate, and that is much greater than the communication rate. Even if we are exploring for larger, wider frequency spectrum, harsh part of the electromagnetic spectrum by means of millimeter wave communications, but still every time there is a scarcity of spectrum, because as I say that huge amount of wireless node to be connected, and for their seamless connection, bandwidth should also be an issues, and that to be made provided the storage and transmission issue can be provided if we have an efficient compression techniques, compact representation of the data, and that not as a post processing after acquisition, that to be in a single platform during the data acquisition or during the capturing of data, we have to do this compression techniques. So as I already told, that all these application specific what we are expecting, that smart home, smart city, intelligent transportation systems, healthcare support, all these are possible because of this promise are coming from the Internet of Things. As far as there are many definitions of Internet of Things in the literature, what I like to say in this talk, I just like to say other way, that it is nothing but a large set of heterogeneous nodes to be connected. They will share data among themselves or with some cloud environment, and these devices or these objects to be equipped with sensor, actuators, electronics, wireless communications, and processing technologies. They will collect data and share for certain applications. As I already say, that there are heterogeneous. So basic objective of IoT is to connect heterogeneous devices and systems to provide low-cost application-specific services. This cost seems to be hardware, software, or in terms of communication, in terms of storage, and all these. Now, as this IoT framework or system emerge, there are a couple of issues come into the situation. These nodes being heterogeneous, they have the interoperability issues. The issues of different computation and different communication capabilities are there. Or in other sense, they will be working not in similar communication or computing resources. They may be operating in different environment, and they will be working in a constrained environment. And as a matter of fact, we need to go for a protocol, a communication protocol or networking protocol. We need to consider about the issues of integration and management of these devices. Apart from that, there would be the issue of scalability. There would be the issues of information exchange, power consumption, interoperability, and system flexibility. So what I'm going to say, that at one end, there are billions of nodes to be connected, large volume of data, storage space are limited, bandwidth constraints are there, devices are having power limitation or energy constraints. So it needs an efficient data acquisition, a compact form of representation, data representation, but at the same time, reliability will not be lost. In fact, we will see later that data representation, compact representation are under conflicting. When we look for compact representations, it will save us in the form of storage, it will save us in the form of transmission and delay. But at the same time, if we see our communication concept or even day-to-day communication, forget about the electrical communications, we see that redundancy in the data is essential for reliability. On the other hand, when we look for compact representation, we throw away the redundant data. We exploit the redundancy already present in the data. So reliability demands redundancy to incorporate. On the other hand, compact representation demands to throw redundancies. So there is an issue that how the compact and optimal representation to be done. So if we just see the IoT architecture, as I already say, that it needs for this application in IoT environment to meet, there is need standardizations. People are working, but it needs a standardization. As a matter of fact, several IoT architectures are being suggested. Say, for example, a 3-layer architecture where it is perception layer, then communication layer, then application layer. Somewhere people are thinking about the physical layer, transport layer, middle layer, and then again applications layers. Somewhere it is again other form of architecture. But however, for to meet an IoT, irrespective of any special application, a general framework of IoT, if we think of, then we can think of these 3 layers. One is the sensor layer, or sort of things data acquisition layer. Second thing is an intermediate processing or transient processing, not very rigorous computation to be done. So intermediate state of data processing, that's your basically the processing layer. And finally, there is the application layer, where seems to be the hosted the cloud, and where it is expected that it has enormous computation facility and others. So the application layer is hosted with cloud, and there are computing facilities. There are not that much of constraints in computation. On the other hand, the sensor to be power driven, so self-power driven, they have limited power, they have limited computations. So they will be having less burden of computation and communications. So what is it expected that in other sense one can think of that can we shift this computation burden from these devices, handheld or small devices, to that computation to the far end in the application layer. Basic objective of this IoT is something like that, to shift this computation, limited computation and communication ability, and that share or shift towards the end in the cloud environment or in the application layers. So if we just see this 3-layer architecture, so sensing layer is basically collecting physical data. This data may be, say, for temperature, or it may be humidity if it is a question of environmental related issues, or it may be the physiological data for human health, like ECG, blood pressure and others. But most of this data, the things that I remarked here is that needs conversion in digital signal. Most of these physical parameters or physical data are analog in nature. They are continuously varying. I will define that what a signal is and why we need for digitization, and for digitization, what is the need or necessity to be made. And as I already see in the processing layer, that there should be a transient type of processing, data processing or storage, limited storage and process, and there should be some computation, and then real-time, or say for example, you can say real-time data analytics, and then this to be uplink towards the cloud. And in application layer, there would be the information routed from the processing layer, and there would be several, enormous computation jobs to be done to meet the particular application or particular service. Now, question comes that IoT and all these application specific things are made possible with the emergence and the promise of the 5G. Now, what is there in the 5G? In fact, what makes the 5G catchy? There are 6 issues in the I would say components that makes 5G very catchy. One thing is the information superhighway, that is the millimeter wave communications. Millimeter wave spectrum, 30 gigahertz to 300 gigahertz, which can be thought of like a superhighway, means large volume of data at high data rate can be transmitted. The second thing is coming into the situation is the MIMO, multiple input and multiple. So the tiny mobile devices will be equipped with multiple number of antennas, and that will provide spatial diversity, multiple independent number of channels. So your signal to be having multiple copies, and the receiver you can combine them to have a good signal. So this diversity, or you can think of the spatial multiplexing facility. So MIMO is another component that adds here. The beamforming issues are another point. So it would be, as the high frequency, it would be more directional. So base station can see your end user very directional forms. So other issues is the beamforming. Apart from that, there are NOMA, non-orthogonal multiple axis. If we see the traditional TDMA, FDMA, CDMA, some form of orthogonality are exploited, whether it is in terms of non-overlapping time, non-overlapping frequency, non-overlapping code. But NOMA is a concept where it is, because you need to allocate more number of users in a resource constrained environment. That resource is the bandwidth. So NOMA is another issue are there. And apart from that, there are the mobile edge computing, or edge computing means you can take away users away from the clouds and split the jobs. Some tasks to be done in the app ends and some to be done at the cloud end. So these are the basic things that makes 5G very attractive. I'm not going to that issues. What I was going to say here: millimeter wave, massive MIMO, small cell, and beamforming, and NOMA. NOMA and mobile edge computing. So second things comes that I say my second part of. So the first part like to say that there are needs of a compact representation of data during the time of acquisition. As I already said that much of the data of the physical devices that will capture the parameters, these are mostly analog in nature. Now for their digital processing, needless to mention why digital processing, because all we know that digital domain representation and digital domain processing offers certain advantage over its counterpart of analog. Now, digitization process involves two things. One is sampling, other one is quantization. But prior to that, I will make an introduction. What does the word signal like to mean? Signal is nothing but mapping. Signal is nothing but mathematically a function. So as it is a function, there will be some independent variable and some, the variable, which is the function. So we can think of signal is something like a form where it is nothing but, a signal is nothing but a time function, or it may be a pace function. Say for example, it is speech like signal f of t, or it can be of image like signal, or it can be of video like signal f of x of t. So these are independent variables, and f is the functional value. Now this x, y, t or f, they can be either continuous or they can be discrete in nature. So any possible combination of these two things to be there. Independent variable x, y, t can be discrete or continuous. F can also be continuous and discrete. As a matter of fact, different form of signal to be there. But as I say, that much of this physical environment data that we collect, our sensor collects, that's a basically analog in nature. But our digital systems likes to get that data into digital form. So this continuous signal or analog like signal, which is a signal as a time function. So this is basically an amplitude variation as a function of time. This needs digitization or discretization. The first question comes to digitize. If I take digitization or an interval, discretization in time at own accords, will it possible to reconstruct the continuous time signal back at the receiver end? Answer is no. We need to make a rate of sampling. We need to make a sampling interval such that there would be, from the discrete set of values, when it is required, we can reconstruct back the original signal. And that, to meet, the question comes is bandwidth. Means what to be the sampling rate, so that from the discrete set of value, we can again reconstruct the continuous time varying signal. It answer comes from a governing principle, that is Nyquist sampling rate. Nyquist sampling. What it says? It says that if a signal is band limited in W, so signal associates itself with a term is bandwidth. Now, what is bandwidth? It indicates one thing, that signal, if it is a time varying function or any change of variable, then there is a point we can think of, that at what rate, at what rapidity the amplitude changes with the variables. Now that other way like to say, when I say that the rate at which amplitude change, very crudely if I like to say, when I have a signal is nothing but a function, one can think of at what rate or at what rapidity the amplitude changes. That associates a term frequency, because all we know that frequency is a term number per second. So in such like that way, when a time varying function or any amplitude change with any variable, so the rate at which change is associated term frequency, or it's associated with term frequency content. Now, once frequency content means some frequency to some frequency, it gives rise to a range of frequency. Now, all frequency amplitude means we can think of a mapping that a time function can be thought of a frequency function. Means this horizontal axis would be a function of frequency and the vertical axis would be the amplitude as a function of frequency. So a time variation can equivalently thought of by means of some representation space. Choosing some representation space, we can represent in its frequency domains. Now, apart from frequency, there are other things also, other representation space also. A computer science people might think of why Fourier and why frequency. Well, for your understanding, and he or she might be more interested, well, I least bother about whether a continuous time varying data or something like that. I'm mostly familiar with a sequence of data x1, x2, x3. I will be looking for some searching techniques or sorting algorithms and all this. Well, think of that this is a data already vehicles. At least the width of the road should be equal to the width of this communication. I mean the car. The width of this, the width of the road required should be equal to the width of this car. So, if your car is a signal and road is a communication channel, so the width of the road must be equal to the width of the communication car. Same thing in your information communication. So I like to ask you to visualize your communication problem as a transportation problem. So the bandwidth of the signal to be transmitted over a communication channel must be at least equal to the bandwidth of the communication channels. Now, what is that bandwidth? Now, as I say that this time variation help us to think of something rate of change. So what I like to see in other way, that if I consider this is an object and I like to see this object through a glass, the glass is something through which I like to see this object. Obviously, the object may be seen in another way. So when this time varying function multiplied with this basis function, so what I like to say, forget about this time being whether your signal is continuous or discrete. It needs an efficient representation space. It needs a compact representation space, and that representation is essential for compact data representations. Now, why this is Fourier transformation and why it is associated with frequency? Let us consider the think of this situation. You imagine that this is white light. When white light passes through a prism, we can see because of the dispersion there are different colors. Now, when I invert this prism and pass through this, we again get back the white color. So this white color decomposed into different components and again back to the white colors. We need data processing. We have data, we need to go for its representation phase for extraction of information, and possibly at the user end for consumption, data consumption or use, we may have to again go back to its inverse representation. So same thing is done here by mathematics Fourier transform. What I'd like to say, if your GT is the time varying signal, I like to see its frequency content. My concern is, if I like to synthesize this signal in lab, what are the frequency component? If I amalgamate them, if I integrate them, this will give me a time function like this. In order to answer this question, rather to see what its frequency content, how much frequency I need to retain for its transmission bandwidth to determine, or how the signal energy contain, or what bandwidth or what frequency, up to what frequency range I have to consider, that answer to be obtained by doing Fourier transformation. So GT, as if it is an object, the glass e to the power minus j omega t. What is an e to the power minus j omega t? I don't include all this in slide, but if you think of the e to the power minus j omega t, you can think of a rotary vector, a vector having angular velocity omega, and if you project on real axis and imaginary axis, it will give rise to sine omega and cosine omega. So e to the power minus j omega t, what it is nothing but cosine j omega plus j sine omega. As an engineer, if you like to physically interpret, it's nothing but imagine a rotary vector, and the vector is rotating platform with an omega velocity, and it gives the real-time projection and projection on imaginary axis. So this gives rise to a frequency domain description, that j omega. And when you do the inverse Fourier transform, so this prism plays the role of Fourier transform, and this prism plays the role of inverse Fourier transform, and this notation implies that they have got inverse Fourier transform pair. What it says, that this time variation, if I like to see what it is frequency content, why it is required. Now I like to digitize this signal by means of sampling, so that from the knowledge of this sample, my receiver will reconstruct this continuous time signal. And to answer this, I need to see its frequency domain content. What is the highest time frequency variation I need to retain, so that my sampling interval or sampling rate to be set in that way. I like to say, as my computer science student may think of, well, I least bother about the data physical parameter which will be in continuous form and continuous change in amplitude. I have only a discrete sequence. But again, you see that suppose you do a pattern recognition problem, a stick you are considering as a pattern. Now you see, in your home, at your room, if you go to the extreme one end of your wall, you can see the floor, and this is the wall. So this, imagine a rectangular coordinate system, and if you put your stick there in this home in three-dimensional space, the tip of that stick can be represented by a set of values x1, x2, x3. So this signal is nothing but a vector. As a signal, when you go for Fourier series representation, if you remember your mathematics class, you will see a periodic function, a rectangular function can be thought of sum from the sinusoidal function, sine omega, sine 2 omega, cosine 2 omega, all harmonics. So this sine omega, sine 2 omega, sine 3 omega, cosine 2 omega, cosine 3 omega, all forms a signal space. Sine, cosine, they are orthogonal, because if we take the inner product over a time period, they will yield to 0. So like your x Cartesian coordinate system ijk, the role it plays, same thing role plays by Fourier series, sine omega, sine 2 omega, cosine 2 omega. So you need, so a0, a1, a2, a3 is like the coordinate of the sine omega, sine 2 omega, the coefficient of that. So in signal space representation, you need to go for a signal space representation for representing your time varying function as a dot point in that signal space. Like here, this vector or this stick can be simply represented by a dot, and if you consider the x1, x2, x3, this value by dot, you can represent this whole thing. So this vector or this signal is pattern can be represented by only this tip with these three coordinates. Same thing, a time varying function in an orthogonal signal space can be represented by a dot. So every pattern what you associate as a computer scientist in appropriate representation space, they can be represented by a dot, and that's asks for you looking for you a representation space. I don't like to say that representation space to be only Fourier. There are many such representation space. Even if you see your vector mathematics, there are three-dimensional space, Cartesian coordinate system, cylindrical coordinate system, rectangular coordinate system. So a vector, depending upon the choice, can be represented, and one representation definitely offers some benefits with respect to the other representation. So for example, here I like to say, if my representation space is x, y, z like this, so x1, x2, x3 all are non-zero value. Now if I choose that representation space is something like this, that this x, y, z red mark is my representation space. Now I can represent it as a parse form. In sense, some of the coefficient of x1, x2, x3 will be 0. So a three-dimensional vector which is having three non-zero value for its representation can now be represented by 2 or 1 value. So it gives us a compact form of representation, a parse form of representation. So that other way, like to say, data needs an efficient representation space for its compact representation. Because if I can go for compact representation, I do have computational benefits, I do have storage facility, I do have transmission bandwidth facility, I do have energy facility for less number of data to transmit, and of course I will gain in delay, less delay will be there. So this is basically Fourier transform and line. Now I will just take one more slides. It looks clumsy because I don't like to add many slides. There are many other slides to. So suppose you are having a continuous time varying signal. It's an analog signal, and you like to go for its digitization. I'm not talking about the amplitude discretization, which is coming in the form of quantization in my talk. I'm just talking about the time discretization, which is called as sampling. So this needs discretization, and how it can be done? I need to consider a function that's called a series of impulse or impulse train. Impulse is something like let me introduce impulse other way first. Okay, maybe I will come back here again. Impulse is something like a function like this, very peculiar functions, which is located only at this value where it is having non-zero value. In all other cases, it is having zero value. It is having only non-zero value here. It is a peculiar function where it is again an undefined. It is undefined. So it's something like Tagore's poem of Pumpty, but it is very powerful. I will come to this powerfulness in due time with some jokes, but go back to that. So series of impulses, and I'm coming back to my old, and I let me remember that's things I will say. So if impulse, rectangular, train of impulses, when multiplied with this gives discrete time signal. We have to have certain condition that this interval should have certain condition to make. Once I say interval, in other way I like to say sampling interval means sampling rate, means number of samples to be taken per second. And Nyquist specifies that the signal whose spectrum is band limited to beta. What is band limitation of this signal? As I say in previous slide, that you see it's a time limited signal, and there is a duality between time and frequency, just like your Heisenberg uncertainty principles. You cannot localize the position and momentum at a time. Similarly, if you localize some event in time, you will lose the frequency information. If you do the Fourier transformation of this, it is theoretically extend to infinite frequency. But you see, the beauty is there that this representation, but my time function, instead of like this, could have been like this. You may say, well, it's a time limited function and the value is going to, so it is compactly represented like this. But there is no guarantee. My time function could have been something like this. But even that signal, if I go for its Fourier transformation, real life signal shows this low pass like nature. In sense, the frequency content go on decreasing, and that suggested that okay, you may not have the full reconstruction of the original signal, because perceptual data you need not, your audio, your speech, your video, you need not have to go for complete reconstruction. As long as the intelligibility is okay, that's fine. So it otherwise says that up to this frequency content, if I take, so much of the signal energy I can calculate. What is the energy? Now, if we just square of this and integrate, because it is a time continuous function, frequency continuous function, so you need to go integration minus W to plus W, square of this, that would give you the energy content of the signal. And if you see your W is set here, energy content will be less if W set is here. So the bandwidth is what? The difference between the minimum frequency to the maximum. This is the negative frequency. Conceptually, it has no meaning, but for mathematical convenience, because there is a e to the power minus j omega t, that brings this negative, and there is a symmetry. So if we just consider this to this is the frequency content, and that gives you the bandwidth. So if your signal is band limited in W, so if you follow this sampling rate, then the time interval of this sampling function is like that, then you can reconstruct that signal. What was your concern? That if this is the value available, can I reconstruct this signal? Can I from this discrete set, can I go back to this? That was the issue. But answer, you see beauty, that the sampling process not only keeps the signal. So this is the frequency Fourier transform, the frequency content of this signal. After doing this sampling, when you do the Fourier transform, it retains the multiple copies of the same signal. What you were fearing, that discretization may lose the information, you will not get back. But if you maintain this rate, if you maintain certain interval, you can see the sampling process gives you the multiple copies of the same. and by anyone to filter out and do the inverse Fourier, you can get back this original signal in time. Now, the problem is what? If this condition is not satisfied, then this one and this one will overlap and giving rise to the problem of aliasing, the term you may be familiar in your computer graphics class also. So that's the point. That's the rate to be made. So what it says that that the bandwidth rate, the bandwidth determines the sampling rate. But in reality, we will see the signal is having two things you need to consider. Communication people may bother about the bandwidth issues, bandwidth rate. And of course, communication people also think of information rate. The computer science people can think of information rate. Means, is the information rate lower than bandwidth rate? I mean, is all frequency container equally important in time respect? I mean, information point of view. If not so, then can we go for sampling on information rate rather than bandwidth rate? So Nyquist sampling theory says that sampling process should be in terms of bandwidth rate. But real life signal, you will see that it's theoretically gone infinite bandwidth, but it's so fast decaying that after a certain time, I mean, information rate is much lower than the bandwidth rate. So if it is so, why don't we go for sampling at information rate? And that is the issue. But prior to that, well, it is possible. Rather than going the bandwidth rate sampling, information rate sampling allow you to reconstruct of the signal much lower sample than the Nyquist rate, provided your representation space is efficient. If you have a compact representation, what I am going for compact, essentially mathematically it is called a sparse representation space, so that at sampling at information rate, which is much lower than the bandwidth rate, sampling rate, Nyquist sampling rate, you can reconstruct. And that gives rise to the concept of compressive sensing or compressed sensing. Before going to compressed sensing, let us once again recap that what is the current or conventional mode of signal or image or data acquisition. When you go for analog to digital conversion, what is the mode of this? What we do? We take Nyquist sampling rate, much higher sampling rate, and we find that our samples are highly correlated. When we do the large sampling rate, Nyquist sampling rate, we see that the samples are highly correlated. I mean, they are redundant information, and we throw that information. So we take the trouble of high sampling rate, we find that samples are highly correlated, there are redundant information, and at later point we throw the samples. So pertinent question comes, can we do sampling at required rate? Means, if I find that out of n samples, there are m number of samples are redundant, so we can throw n minus one m number of samples, then why we will not take only m number of samples during the data acquisition process? So the things comes into the scenario is that the current mode of things are capturing, or the sensor or actuator, or I mean the sensor devices that captures data, sampling at night. Now it suggests that difficult to capture if you have a wider band signal, if you have a particularly in the space, or particularly in the remote sensing, the video or image like signals, the bandwidth is so large, the sampling rate is very high, and the analog to digital hardware platforms are also having problem. That was the optical signal processing, and digital signal processing was the limitation of the sampling rate. So why don't we think? So the Dono says this, as I already said. So why not we go for a compact representation, or say single form of states, compression and sampling, or compression right at the time of sampling? That gives rise to compressed sense. So what is requirement is that we can take random measurements. When we capture the scene or the signal, we capture the signal in a compact representation space, in a sparse representation space. We have to look for our data of interest or signal of interest to be represented in a part. That's an important research. So what in other way like to say, the question that I raised already, that why do we take n samples when we only need n samples? or can we compress right at the time of sampling? Mathematically endpoints. So let us forget about the signal processing aspects. You can think of like that way. You have an endpoint data x1, x2, x3, xn, but you need some compact representation in order to achieve benefits of your IoT sensing devices in terms of storage, communication, processing, delay, and all this. So your x1, x2, x3, xn to be represented by x1, x2, x3, xm, where m is much less than n. And your reconstruction at the far end, when it is required at the application layer in the cloud environment, there is enormous computation. You can go back inverse problem from m point to n point, means from x1, x2, xm to x1, x2, x3, xn. Look about our mathematically, this is called an underdetermined problem. Why? Because in your school mathematics, you see that when you do for solution of two variable equations, you need to have two equations for finding two variables. If you have only one equation for two variables, what you could do, take the value of one variable and put that value and find the other value. So you have theoretically infinite number of solutions. So here also, when you make an attempt for m point data to go back to n point data, you could have theoretically infinite number of results. In other sense, it like to means that you have less number of linear set of equation than the more number of variables, and you have large number of solutions. Out of that many solutions, you define a target or application. Choose the best one for your application to meet. So it's some form of constraint optimization need to solve. So you have an endpoint data actually. During capturing, you only capture endpoint data. That is essential because in many situations, for example, medical MRI imaging, it's so slow process. It takes 40 minutes of time. And keeping your pediatric person or a old person in this longer duration during data acquisition is very difficult. So it is possible that if you can take less number of samples and then dump these stats to your computer friends who will reconstruct back the endpoint data. So it's essentially what it's like today. Your IoT sensor will capture only endpoint data, and because of its limited computation storage, and this will go to the cloud, and cloud will do its exploit these computations and reconstruct back the original endpoint data. To meet that, there are two essential requirements. One is sparsity. What does it like to mean sparsity? Sparsity like to means the time and again what I'm going for a compact form of representation. Means if your signal, if your data points is represented or projected in a space where only certain number of coefficients are non-zero. So a signal is said to be k parts provided, or a sequence of data is said to be k parts provided k non-zero coefficients are here. This is one requirement. So CS or compressive sensing, and from here the full reconstruction is possible provided you have a sparse representation space. You take the random projection, you take the random sample from the suitable representation space where k number of data are sparse, means non-zero, or at least the signals are compressible. I do not use this term, include this term mathematically. By compressible like to means the discrete sequence, the value should be numerical values, or the coefficients should go on decreasing in a power law. So the values are going decreasing such that it can be thought of like a compressible. So k sparse or compressible. So if you have a representation space of sparsity or compressible, one state is okay. Second thing is incoherence, means from this sparse representation, I mean when you have an endpoint data, you have a k point representation, and this k data, if you take random projections and then you go for, so you can, random projection means random sampling. So it needs a random sampling functions. So that's called a sensing function. So you have a representation space and you have a sample collection space, sensing function. These two spaces should have incoherent, means their correlation should be minimum. So representation space and sensing domain to be uncorrelated. If they are more uncorrelated, less number of measurements will be. Now, before I go to show what is representation space and what is sampling or sensing space, just imagine I show you the palm tree-like structure of impulse, which is very localized in time. It is frequency domain, have you ever seen, that is spread over wide spectrum. So it is one sense incoherent. What is localized in time, it is spread over frequency. So what is requirement? Suppose you have a sequence x1, x2, x3, xn. You now go for a representation. You need to have a psi, the basis function, or the representation function, like your I, j, k in Cartesian coordinate space. That's the basis vector. Like your sine omega, sine 2 omega, sine 3 omega, cosine 2 omega, cosine 3 omega, which is basis function in Fourier representation space. You have to look for some representation space, and I say this representation space is psi. That may be Fourier transform, that may be discrete cosine transform, that may be wavelet transform, and very many variation of wavelet transform. Discrete wavelet transform, curvelet, contourlet, ridgelet, bandlet, like the way that's the signal processing people do. Like the name of Lord Krishna have 108 names. They like to look for explores for different space of representation by choosing different transformation function. Similarly, you have an endpoint data here. Suppose you think of a representation space. Let's say this is Fourier basis, e to the power minus j omega t, when it is my gt time function multiplied or xn or gn discrete sequence. If you do it summation operation, so this is your Fourier coefficient, and when you do the inverse Fourier transformation, you can get back the same. So this is your Fourier transformation. This is the Fourier coefficient. Here you can think of your path representation. So your x1, x2, x3. Here you do not know. All components are equally important. You cannot throw your data. Suppose you have a sequence x1, x2, x3 endpoint data, but their numerical values are such, apparently you cannot see which one is important and which one you can throw. But if you do a representation space, like your vector, as I saw, in certain representation of current, but when I rotate the axis, I could have a compact representation, or I could have a sparse representation. So this basis allow us a sparse representation. So out of this, remember that if this is an endpoint data, SI is also endpoint, but out of this endpoint, there are k number of points which are non-zero, rest are zero or very small value. Don't be get confused. If you have a sequence x1, x2, x3 endpoint data, by doing discrete Fourier transform, you are having endpoint discrete Fourier coefficient. There is no reduction in length, but the representation space gives you benefits that some of the coefficients, numerical values are so small or zero, you have a sparse representation. And now you do the inverse Fourier transform, you can get back the original signal, lossless form. So you can think of an orthonormal basis function. This basis is Fourier transform, discrete cosine, wavelet, ridgelet, bandlet, contourlet, as I said, different type of Wall-Sedamar or something like that, different transformation space. Now, coherence, as I already say, so it is your representation space, the Fourier transform, and this is your sensing, like your impulse function. So in a two-dimensional signal, if you consider a two-dimensional representation of impulses. So this is your sensing matrix or sensing function, and this is your representation function. Requirement of CS is that, second requirement is that, so first requirement is sparsity. That second requirement is what? They should have minimum correlation. How do we calculate? Now any two values between two elements, the correlation, the maximum correlation. So it is measured by inner product of two bases. More incoherent the sensing matrix means less measurement is required, right? As I like to say, that's an important point, that your time varying continuous signal when multiplied with this is the discrete sequence. Now my requirement is incoherence to say. You see it is localized in time, very specific in time localization. But as you see its frequency domain description, it's spread over wide spectrum. All frequency, this is the frequency axis, and all are equally important. So what is localized in time, it is spread over. So this is your representation space, and this is your sampling space. These are uncorrelated, I mean incoherence. What I am going to say in jokes, you see this impulse, have you ever communicate by blinks of an eye? Blinks of an eye can be thought of like a impulse. You see what an enormous communication it does. Danger is there also. Its spectrum, you see, widely spectrum. Is that jokes, nothing else. Okay, So I will just go for a compact, CS in theory. What it's like to say, actually CS theory is very difficult. Mathematics are there, convex optimization. I do not like all this to say here. What I am going to say here is that you have a signal X. Remember, it need not be a continuous time signal. As you are computer science people, you like to see it as a sequence. I think it is a sequence, X1, X2, X3, Xn. And your Xn, this is your Fourier transform, discrete Fourier transformation. So this is the Fourier basis representation. This is your sequence. When you just, but eventually this may be analog, and you have to do sampling, and you have to do compact, look for this compact. But even if you are in discrete domain, you can again go for compact representation by choosing for representation basis. So this is your purse representations. You can see that some of the places are void, means this is zero values. Now, when you are having a m cross n, so this is your endpoint data. When you do the Fourier transformation, you are having the endpoint data, but some of these data are zero value and giving k sparse. So k positions are your non-zero value, and the indices of these are called support. I'm not going to this level. So now you are having a sensing matrix. This is again a design issue in CS, but consider this is an m cross n matrix, your design matrix. It has certain property to satisfy, but imagine it is nothing but a m cross n matrix. So your m cross n matrix, when multiplied with n, it gives rise to m measurements. These are called measurements. What it physically like to say, you are having an endpoint data, you are doing discrete Fourier transform, these are discrete Fourier coefficient, and from this discrete n Fourier coefficient, you are taking a random projection, you are randomly choosing m number of measurements. How you are choosing? Now you are multiplying these Fourier coefficients by a sensing matrix of size m cross n. Now your concern is, can I go back from here to here? It's an underdetermined problem. When from here taking help of this, if you multiply inverse of this with that, whatever you will get of S, that's not unique. There are many S, and what you need to do, you have to do a constrained optimization problem. Choose that S bar, which will under the constraint such that y is equal to this. Y is this measurement. So you have to do these convex optimizations, and you will get the reconstruct back this. Because once you get back S hat, what is the discrete Fourier transform? From the measurements, you are getting back the discrete Fourier coefficient. Now you do the inverse Fourier transform, you will get back the origin. You will get back the reconstructed signal. But when you go from here to here, by taking help of this, inverse of this, you will not get unique S. Every time you are having different S. And you choose that S hat, you select that under this optimization framework. And that S hat, when you do the inverse Fourier transform, you will reconstruct the signal. So that's the CS theory. In fact, there are lots of algorithms. Convex optimization one framework, other one is the greedy algorithms. And in this research, computer science people now coming and contributing in terms of reconstruction algorithms. I just talk here only the three things. That's the convex optimization framework. And I didn't show you the pictorial diagram that L0 optimization. L0 optimization like to means you look for the first k number of coefficients, k number of non-zero coefficients. Low value, the lowest non-zero value. That's the L0 optimization. Means from lowest L0 or lowest non-zero coefficient, you like to reconstruct that. Means you are having which minimum non-zero value from where you can reconstruct value back to the endpoint data. It's a combinatorial problem. It's an NP hard. But if you could do so, it could provide us the parsed solution. I have written here parse, but actually it is parsed solution. It is difficult to achieve. On the other hand, if we go for L2 minimization or L2 optimizations, that's energy, that doesn't provide you the optimal solution, parse solution, but it is convex optimization, it can happen. In between, this is L1 optimization. Physical meaning of this L1 is what? Now you are looking for those non-zero coefficients such that the sum of the non-zero coefficients should be minimum. So you are looking for this reconstruction problem. You are while mapping from measurements to S, while you are going from here to here, from here to here, you are essentially doing what? You are essentially doing this optimization. So this is providing you the solutions, and that's convex optimization and linear programming or sort of things. Convex optimization, you can make use of that and find the solution. There are also greedy like algorithm, as I say. So this is basically called basis pursuits. This is the basis pursuit. And if these measurements, when you capture your sensor, is electronic devices, in spite of the best sensor, there will be measurements error. That is nothing but your noise. So if your measurements is what? Now the samples we randomly keep up from the parse representation space. These are called as measurements. So when these measurements are noisy, then we will have this optimization in the framework that the constant change to this is the bound of the noise, and this is called basis pursuit inequality constant. So these are all different algorithms. I'm not going to all this indeed. Now, in order to show you the flavor that how CS works and how it provides the storage and transmission benefits, just to give you, take the image, because image is perceptual signal. If I throw data, keep data, how much I can retain, it's very easily to be shown. So for an image, you know that there is age-like information. So you can calculate what is age. Mathematically, age is nothing but the derivative operator. So when you use a filter or whether you apply operator over an image-like signal, you are looking for a filter or a kernel whose coefficients give rise to derivative operator. So this is basically is your GX. So what you are doing, suppose you are having a pixel, this one, and this one. So horizontal, you are taking difference. So that's your delta X. When you take the vertical difference, that's your vertical age, dy. And now if you have a square root of gx square plus gy square, you are having a simple way, the calculation of the age. Now total variation. So if you are having age, you just go for minimization of age variations. And that way you solve your optimization problem for cost. So total variation, just you calculate the age or total variation, TV minimization, which is called. And if your measurement is contaminated with noise, then you can go for your TV2 sort of things in form of like this. So this is basically TV1 minimization in the sense, if edges are less in number, sufficiently less, then by this algorithm we can reconstruct back the original light signal. Now if it is noisy, then you go for such constants. Your constant to be something like this. Algorithm is used for recovering image from noisy image. Just to have an idea, you are having a signal where I just represent them by endpoint, means one-dimensional representation, 31,068 pixels, 684 pixels. I only keep 10%. 10%. Imagine that the value is 3168, like roughly. This is the quality, and this is 20%. This is 30%. This is 40%. So if you look for a progressive quality access control mechanism based on the available bandwidth or storage space, you can control your measurements, and you can go for energy saving way of data transmission, storage, and reconstruction. Similar things I saw for another image where it is 50,000 like, and when you look for 10%, you see this reconstruction. When you go for 50%, this reconstruction. You could not get this ratio of compression and quality in standard compression techniques. Not only that, in compression, you have to take the troubles of high sampling rate and then throw it. Onboard processing to be very high. That compression tasks to be done, and that is again energy consuming. So this is another techniques like that. Now, what I'm going to say, in IoT framework, there will be large number of sensors. Say, for example, WSN based IoT implementation. There would be densely deployed the sensors. Now, if we think of that only one sensor, you will exploit the intra-signal parsing, intra-signal correlation. Just something like image and video. If you see an image, there is a correlation among the pixels. One pixel can be predicted from the neighborhood values of other pixels. So, interpixel redundancy. And that we use in compression. Now, if it is a video signal, you could find the redundancy from one frame to another. Similarly, concept, this compression, I would say, is used in distributed compression. What if you have more number of sensors and they capture similar light signals. So apart from intra-signal sparsity, we can exploit inter-signal sparsity in many situations. Say for example, or other, I mean, glucose level and all these, when multiple sensors are used for capturing, so these data should also have certain form of correlations. In other side, like say for example, humidity, temperature and others in systems, if you like to go for. So even if there are multiple sensors used for capturing the data, but it is expected that there should be some form of correlation, and that correlation can be exploited. So inter-signal sparsity structure can be. Now when you go for DC, now it's a work of computer science. You can now think of how it can be implemented in DCS, I mean distributed CS. You can think of that sensors are independent, means during acquisition they do not collaborate, they only capture their data and they do not, so they reconstruct individually, and then you can choose which one is better at a particular time and take that one. That may be one approach. Or other approach can be, during capturing they are independent, they capture independently the parts data, but they send it to the fusion center, and fusion center amalgamate them. So fusion center exploit the inter-signal and intra-signal. Intra means individual signal sparsity, and inter-signal means one sensor signal to another sensor signal sparsity. Signal sparsity can be exploited in the second approach. So the last part of my talk, that is compressed sensing based IoT. Now, the first thing what I like to say, so in architecture level, as I say, that in IoT architecture there are several layers of architecture, but in my talk I only consider three-layer architecture. One layer is sensor layers, where heterogeneous sensor will be collected the physical data and will exploit the sparsity. Some data to be routed to the intermediate processor or processing layers. I mean, that is their mobile edge computing and something like that, where the I mean chip computation and others can be done. And after that, that's my processing layer, and then it goes to the application layer, which to be hosted with your cloud. Now, first things I need to answer, that why CS or how CS can be made use in IoT. As I say, that in IoT, the first level is the sensing, data acquisition, and most of the physical level data, real world data, which will capture temperature, humidity, ECG, EEG, blood pressure, and all these physical phenomena, physical data, this can be represented partially in some suitable representation. Now, you may ask the question, is there any unique representation where all this? No, the answer is no. Or when we do the Fourier transformation, the basis function is fixed, e to the power minus j omega. When we choose the DCT, discrete cosine transformation, basis function is fixed. Even for DWT, basis function is fixed. Now, what can be done? Which will be, I mean, my data space at hand, in which representation space it will be partially represented. It's again an issue of dictionary learning, and people are doing so. But it is true that IoT sensor, what data this will capture, it can be partially represented. So, as I say at one point of time, the whole objective of CS-based IoT platform is to shift this computational and communication burdens to this end, where there are enormous companies. And this is possible exploiting two properties. The first property is what? Sparse representations. The physical data can be represented in sparse space by suitable representation. And second thing is the architecture sporadic transmission, means all sensors should not be active in all point of time, because we may say these sensors are essentially connected wireless means through them as well as this computing environment. But some links are so poor, or some sensors are so poor in their contribution may be less. So we don't need their contribution to always include. So fusion center may ignore their contribution. So if we can regulate the activity cycle of the sensor, by that way we can save energy. By that way we can enhance the lifespan. So what I'm going to say, there are two issues that suggest, that say that compressive sensing can be made use in IoT design. One is your, as I already said, that DCT, DWT kind of representation space. And second thing is sporadic transmission scheme that most IoT platform exist. That means not all devices transmit simultaneously to fusion center. Architecture sparsity can be exploited. Remember, the architecture sparsity means at one point of time, some nodes to be effective and other to be in sleep or in silence mode. So network architecture can be exploited. So these two attributes make CS potential to IoT implementation framework. Now, first level is the sensor level. As I say, that sensor, actuator, RFIDs and communication technologies all are there integrated, right? And particularly if we see, there are hardware and software heterogeneousness are also there. Basically, the hardware is made by RFID and wireless systems, the two, realization. Now, RFID, if we see, that basically consists of RFID tag, which is having an unique identification code, and it also having a scanner which read the device. So RFID reader, right? Now, what would happen? This can be again to be placed inside the body or on the skin, or it can be somewhere. Even if the range of this transmission, so this RFID they provide, capture the data, provide the storage, tracking of this, and as well as communication, low range communication or low limited range, but this is also used. Now, on the other hand, there is WSN, wireless sensor network based application. It can be used in outdoor as well as the indoor. Say, for example, in outdoor, when we look for its smart city, humidity, temperature, and all this to be captured. In such situation, or even in case of indoor, when you have the health monitoring system or as well as the temperature monitoring and all this, what we can think of that large number of sensor devices are there, they are continuously capturing the data, so there should be redundant data, and that sparsity can be exploited. Now, wireless application, whatever wireless sensor network application can be easily mapped or to be adapted to the IoT application. But there are danger also. There are problem also. Problem in the sense, in wireless sensor applications, the nodes are basically captured similar type of data. So these sensors are identical and they are capturing a single physical or similar type of data. But in IoT, the nodes are sensors are heterogeneous in nature. So in WSN, so what I was going to say that whatever WSN applications are there that can be easily adapted to the IoT, but the issues are there in WSN. Sensors are homogeneous in nature. On the other hand, in IoT, the sensors are heterogeneous in nature. Furthermore, if you are not properly placed the nodes, deployed the nodes in WSN, the performance will go, but lifetime will also go like that. So some research needs to do it in order to incorporate or extend this wireless sensor network in the framework of IoT application. And what we can do in sensing layer perspective, how CS can benefit? Adaptive measurements. As I say, large number. So dense wireless sensor network where the nodes are densely deployed. So what we can think of that how much sparsity we can exploit. The question is, if you go less number of measurements, you will have much gain in the storage and transmission, but again reconstruction will suffer. So it needs an optimization problem. That one hand, less the number of measurements, you are gaining in terms of storage, transmission, delay, but reconstruction quality will be poor. So you have to go for an optimization. Then what would be the required number of measurements such that the required quality to be made? So to determine optimal number of measurements, I will cite an example, a case-based example here. Now, say multiple sensors are there. So individual CS data transmitted to the fusion center. Now fusion center can do an weighted combining. So weighted optimal weight can be designed based on the quality of the sense data of the or quality of the sensor. The fusion center can allocate weight. So optimal, so distributed compressive sensing and optimal weighted measurements. CS-based data gathering, you can think of a multi-hop network where nodes will collect data on CS. So CS data will be collected by a node, and that CS data to be transmitted to the next node. By that way, it will go on, and sinks node should have all CS data. So by that way, that CDG, that CS-based data gathering or compressive data gathering, disperse the communication and computation resource. So what I'd like to say is that nodes does CS, and whatever CS measurements one node captured, it transmits to the next node. Next node will take its and this one. So like that way, a sync node have the all CS data from the different nodes. Now sparse network architecture, as I say, that few sensors to be active in time slot, and CS-based routing protocol. You can apply a greedy algorithm while establishing the route setup or channel setup. So channel, you can sense which frequency is available or not. I will come to these issues on the context of spectra. So routing in the set, that greedy approaches to be there, path to be selected in such a way that the measurement matrix and sparse matrix should have the incoherence. Now, one example, as I say, that weighted combining. Suppose you have a sensor, some of our typical applications, what we have done, compressed sensing image reconstruction, that you are having a same scene, you are having a multiple cameras, and this camera is having different focus and from different field of view. So I assume that there is a moving platform because these cameras are in a mobile environment. So some degradation will be there because of the relative motion between the scene and the capturing element. Now, this is my degradation, and this is the sensing matrix. So we have the CS data of individual camera, and then we send it to the fusion center and go for a linear regression methods for optimal combining techniques, so that we have a good reconstruction quality. So mathematically, what I'd like to say, my measurements, and you imagine that I have m number of measurements, but again, that actually my signal is endpoint data, and I am having m number of data for CS measurement. I capture m data from this, and that way we just amalgamate, and then we have weighted fusion techniques, and this weight is calculated by means of any techniques can be done. It is linear regression techniques or something. As I already say, suppose if you are having a communication channel and you are doing some form of diversity techniques, so you can think the signal to noise ratio. One can think of like a signal to noise ratio. Just one. हाँ सर, हाँ point of हाँ ठीक है, okay. So this is basically your one approach is one can think of it. Now spectrum is an important issue. Apart from the data acquisition process, apart from the data acquisition, seamless connection is essential for IoT application. So in such cases, how the spectrum information to be provided? One concept is the cognitive radio. In cognitive radio, we can think of that there is a primary user who is actually having the spectrum. So a IoT nodes before transmission will sense the frequency which is available. And one application is the spectrum sensing. So if you think of an application environment where this IoT nodes as a cognitive radio framework, cognitive radio IoT framework, they are monitoring the primary user activity, and they are making sense sample are transmitting to the fusion center. Fusion center makes a global decision whether spectrum is free or not. Sample collection does not incorporate or much energy. Rather, the energy consumption is because of transmission of this sample from this place to the fusion center. And this is a framework which is done by this. What we have done here, the sporadic transmission, that some of the sensors, some of the channels are very poor. We don't like to include. Fusion center give a feedback signal and say that you need not have to transmit, and by that way we can have a sporadic architecture which can be made use. Similarly, mobile edge computing, as I say, that basically the some part of the task to be split into two parts, and app or something like so. It does not otherwise like to say that it does not delimit the use of cloud environment, but some of the transient data analysis or real-time data analysis is done here. And one typical application which I'm going to say here is that the secret image sharing approaches, and for intermediate says, particularly in the physical, I mean the processing layer, the having less computational facilities. So what it is done, instead of doing compressive sensing in your parse representation space, looking for DCT, Dept, and all this, we think of a parse representation in original domain. What I'd like to say, you are having image, you represent a prediction based image, If your prediction is good, the difference between original image and predicted image are very small, and that's give you the sparse representations. So if you like to share this image as a secret, instead of make this share in this form, you just calculate a predicted image, take the difference, and that would, if your prediction is good, so prediction would be worthy, and you can go for this. And that way, you see, this is the cloud environment. Some of the information you can store here, the sensing matrix and all this, and you can reconstruct that. By this way, you can have a facility of your security aspects. And this sensing matrix is very important. If the sensing matrix is not available, it other way, I mean, unauthorized user which is not having this sensing matrix cannot reconstruct this. I mean, this we have studied in other works, that non-availability of the sensing matrix, how it affects the reconstruction of the signal. So if a user is not having the knowledge of the sensing matrix, cannot reconstruct back the signal. So this way one can think of like it. Now in application layer, as I say, last layer, so although the CS was developed for sensing and aggregation and all this, but this is also used in other applications like identification and detection, in multi-user communication. Multi-user communication is a receiver techniques in CDMA. So in CDMA, there are multiple users, they share the same time, same bandwidth by orthogonal code. But still, orthogonality in code, when breaks, there are interference. So this multiple access interference, we can go for sparsity representation. People have gone that, and that way it can provide the detection and identification. CS-based cloud storage, as I say, that you can only put k number of queries, and only k number of queries can be essential to retrieve back that. So this is basically application specific layer, and I just take two examples of remote healthcare support by CS-based IoT. Like one thing is, just instead of going in this, say for example, these days any talk will not be complete if there is no kind of machine learning approaches. And of course, I like to say at the end that CS, IoT, CR, machine learning, they to be integrated in single framework. So for example, if you have a low resolution image and you like to generate a high resolution image, and this to be done in a sensor network, and you do not have a luxury of computation by doing fast representation of DCT, Dept and all this, you can simply go for low resolution images by phase domain, and from there by means of CNN, convolution neural network, and this is a generative adversarial network. This is the GAN generative model, and this is the reconstruction, and by exploiting that you can reconstruct the signals. So this is a CS framework of reconstruction in original space. One such application, you can have remote healthcare support, pneumonia detection. This is a chest ray image. You go for sparse representation, and what is done when sparse data, say for example, somewhere, the remote end the patients are there, the sparse data is transmitted to the city or elsewhere the doctors are there. Now there are two ways. The computer aided diagnosis, instead of full reconstruction, this is for doctor will diagnosis from here, but this CS data and in the CS measurement space, that means even in the compact measurement space, people can do the CNN network for detection. So this is a classification problem, whether it is pneumonia patient or non-pneumonia. We do not even bother about mapping of the inverse mapping of Engg. Even in the compact representation space, we can reconstruct that. So this is CS classification or CS diagnosis, even without going back to the in space. And when it is required for medical practitioners or medical persons' opinion, we can go for reconstruction and make diagnosis. So that's all what I'm going to say at the end. It is the summary. What I'm going to say is here that basically, so CS IoT design research work is done. So energy is very important issue. Energy harvesting can be incorporated in IoT nodes. Implementation in multi-core framework. Then CS encoder design, as I say, that it's very, very important things, looking for the first representation space. And all these work, the machine learning, dictionary learning can be made use. And it is optimal power allocation for CS measurement transmission. As I say, data security, because structured sensing matrix are non-available. Now, encryption techniques, in encryption techniques, the CS is also used. Why? Because your data, in original domain, you are not capturing. You are capturing the other representation phase, and you are taking random projection. So it essentially adds an encryption. So CS adds an flavor of encryption techniques. So that's all which I like to say, that in future there may be an integration of computer sensing, IoT, machine learning, cognitive radio, all in a single platform, and that way for the application specific design to be done. Thank you so much. I think I take too much time.
Well, thank you, Professor MAITY, for your very informative talk, highly illuminating talk, explaining all the basic techniques of this compressed sensing and how it can be applied onto different IoT applications. So, although there is, everything is online, and all of us join Professor MAITY to thank him. Applaud.
Yeah, thank you, Professor,
Thank you, sir.
for
Thank you, sir.
such a
Thank you,
nice
sir.
presentation and taking time in the weekend. And 5G IoT coding are pretty much hot in the area. And thank you for introducing such a nice topic to our faculty and students, sir. Thank you very much, sir.
It's my pleasure. Thank you so much, sir, for inviting me and giving me this scope of.
No, let us. Uh,
Hello.
Yeah, sir.
Yes.
Your voice is
I think
breaking.
Horse had some question. Horse Sina has raised a hand.
Yes.
Is having any question? Yes. Oh, he's left the meeting.
I think.
Yeah. Any question?
I think there is no pending questions.
Oh, there is no question. So that means the communication is useless. The receiver has no impact of this data transmission.
You can stop presenting then.
Okay. Okay. So if there is no question, so I think we should. I think I.
Yes.
I.
And
Yes.
Professor, please share the slide.
Okay. Okay.
If you can.
Yeah. Sure.